presentation, I think I'm here to give you the light relief, folks. What I'm going to talk about is recreational water management and really just introduce some fairly recent data which we're finding trouble in the effect it has on the standard systems currently in force. So I'd like to give a fairly rapid run through of where we are and then concentrate on the problems we've got with this new data that's emerging, if you'll bear with me. The slide sets are available to everybody, and like Paul, I'll be available over tea today to have a chat if you'd like to run through any particular problems. Funding groups, this is really a culmination of about 20 years research, mainly European funding, but also UK research councils. NERC and EPSRC are two UK research councils, but I'll not bore you with all the acronyms. But the background is this. We've got new standards produced in 2003 by WHO, which is the document in the centre. That standard system is based on evidence from what are called randomised controlled trials of people who go to a beach, half go in the water, half stay out, and then you look at the disease differences between the two over a period of 3 weeks. Fairly simple design, works quite well. And that produced these standards for recreational water produced by the World Health Organization in 2003. These are the values here. Therefore, enterococci, they're all 95 percentile values, and the top one here represents a risk of 1% gastroenteritis. This one, 200, 5%. This one, 500, 10%. And generally speaking, it was felt that more than 10% risk of GI by going to a recreational beach was probably unacceptable. Now, the EU took those standards almost directly and used them, but they were a very significant improvement in water quality in Europe, but with the improvement goes very large cost and difficulty in compliance. So to give you an idea, the best standard in Europe on our 1976 directive, the guide value, had a disease risk of about 5%. When you move to the best standard now on the 2006 directive, it's 3%. So we've nearly halved the risk by going to the best standard in Europe. Just the bare compliance level in 76 was 16% GI risk. Going to the bare compliance standard now, it's about 8.4% GI risk. So you can see we've really tightened things dramatically with the WHO standards in Europe by applying the WHO work. But that causes real problems. And it causes problems in places like Wales, where I come from. And it was a very good attempt at Aberystwyth. I'd like to congratulate you on the attempt there. It's very good. But basically, this is just an example of one catchment in Wales. Now, this is one of the best ecological catchments. Anybody knows the area. It's right in the southwest. There's very few people. It's mainly sheep. But what this suggests is these are the values for water quality in these rivers during the summer. You go and sample them every time the river comes up after rainfall, if you like, described as in spate. You've got rivers here which have got an average of about 1 million coliforms per 100 millilitres. That's about the same value as you would get in a discharge from a combined sewage overflow. So our rivers, with no human input in many parts of Wales, are heavily polluted at about the same level you would expect from a sewage overflow. And they are pristine, good, ecological rivers, but they have high microbial loading which would fail or generate failure in a bathing water or a shellfish hygiene water. So how do you manage that whilst achieving the WHO standards? Well, I won't say get out of jail, but the mechanism that has been decided to try and manage that situation is called the Annapolis Protocol. And the Annapolis Protocol basically says if you can predict when those elevations are going to occur and you take a sample during that period, then provided you've warned the public and given them informed choice, you do not count those elevated concentrations in your calculation of compliance. Another way of putting it is sample discounting. And it works very well. For an average beach, you maybe get 2 or 3 of those in the bathing season. If you can predict them, and you can therefore discount them, you've got no high values in your data set, so your beaches tend to pass much better. Now, just very briefly, I'm going to go down and explain the implications of that discounting provision and the problems of trying to model bathing water for those peaks, which at the moment we don't do. But I think we've got a way of doing it, which I'll demonstrate to you. But two other outcomes from the 2006 Bathing Waters Directive was that the Commission agreed in writing in the directive to sponsor further epidemiology, i.e. health studies, and it wanted those in Mediterranean and fresh waters in Europe because there was not much data for them. It also agreed in writing in the directive to investigate whether viruses should be used as compliance parameters in bathing waters. I want to give you a little bit, very, very briefly, the results of those two investigations. And they were conducted in Spain here. There's Maria Figueres. The two sites were Tarragona and Sant Pere Pescador on the Mediterranean coast. And they were using the UK questionnaires, the same methods. So they were randomized controlled trials. It looks very intensive. These are the bathing zones here in Spain. And people bathed and the water was sampled in the bathing areas here. They were in the water for at least 10 minutes. They were asked to immerse their heads on 3 occasions. And we then followed those people up at 1 day, 1 week and 3 weeks after they were exposed. And obviously the bathing group is compared with the non-bathing group. So that was the approach there. It was also done in Hungary. This is Michael Kada on the left, who's now retired, and his team. The number 2 in the team here is Marta Varga, and she's now leading the Hungarian representation on the bathing water programme in Europe. And that was in 2 riverine sites, very different sites. And those were riverine sites chosen because they all had Euro beaches or European identified bathing waters at those sites. Now, very briefly, the outcome from those 2 studies, and this is in terms of the relative risk of illness at the 2 studies. I'll explain now. This is, first of all, for marine bathing waters. This is the Spanish and the UK data combined. And at the end of the studies, what we found was about 3.5% risk of illness. The old EU bathing water best standard in 2006 was about 3, so not much change there within the error bars in this kind of work. For the marine bathing water at the what's called the good standard now, which is about a 5% risk of illness, we found with the new studies that became about 4.5%. So again, a little bit of variability, but the outcome of that work was that Europe would not change the standards and not recommend to WHO that the standards should be changed. So the World Health Organization reviewed that in 2009 and said our standards of 2003 look about right. In terms of excuse me, the worst standard, as the 2006 directive, that was 8.4, as I said before, and with the new work, it looks as if that might actually be slight improvements at the worst water quality of about 5.3. But generally speaking, the rationale with that work was we won't change it. Now, the second piece of work I mentioned was to look at the potential for viruses, things like norovirus. It's the most common cause of gastroenteritis in the Western world. Should we have a norovirus standard for bathing waters? Now, as many of you will know, you can only test norovirus by what is called quantitative polymer chain reaction test. It's a molecular test for strands of DNA, okay? So that work was undertaken in Brazil and 5 European member states. The European member states were about the best virology labs we could find in Europe. This was funded by the European Commission, as with the epidemiology, large-scale European collaborative projects. We didn't recommend moving to a virus standard, and that was accepted by the Commission for this reason. On this axis here, what you've got is sewage being tested for norovirus. And this is the result from each lab. That's the mean value, that's the range, or 95% confidence interval on the mean, in fact. Now, what that data says, and each of the lab was given the same solution exactly, and they got some very different answers. So in sewage, we couldn't get the same answer from 2 labs. This is mineral water that was seeded with the same mixture, and you can see here we've got very different answers. So what that means in laboratory measurement terms is we've got to do a lot more work on getting the laboratories consistent before you can produce a legally required standard for bathing waters using these qPCR molecular tests. So that was the result of the research for the European Commission. And where does that lead us to? Well, it leads us to a WHO document that reported that work, and it leads us to the European directive, which did not recommend any change at that time. Now, as we move forward, this puts emphasis on this prediction of these changes, this real-time prediction and sample discounting. Now, in the UK, and I suspect it's the same in many parts of the world, the UK government has to do two things when it proposes a policy. It has to propose or bring forward the empirical evidence base, the science. It also has to have an independent assessment of the cost. Now, Britain estimated that not the cost, but the benefits of prediction of its bathing water quality in generating more compliance for those bathing waters here was about 1.5 to 5.4 billion pounds. Now that is, it's fiscally important to a country like Britain. We're currently arguing about whether we can afford a salary increase for the public sector. The government's saying no, and that would only be about 6 billion. So, these are quite important figures, let alone the impact on the individual resort towns who will be damaged by non-compliance if we don't get prediction. So this is quite an important factor for the UK water industry and the UK government. And if it has a big impact on compliance, then clearly it's a benefit we want to grasp. But it's a very difficult job to grasp that benefit for the reasons I'm going to outline now. Some places in Scotland had the first attempt at this, and what they do is they look for rainfall or river flow in adjacent rivers, adjacent catchment areas, and they try and predict when the beach will be non-compliant. And they put these electric signs up at the beach, which basically can say, we don't advise bathing today because the water may be polluted. Or they say, it should be okay, the bathing water should be clean. It doesn't work very well. There's a similar system operating in North America called the Nowcast system, which operates by the US EPA. Both systems use simple statistical tools. And asking colleagues last week in North America, how are your models working? Well, for the modelers among you who will be used to things like explained variance, the things you predict the variability at the beach from, like rainfall, is explaining in those models between 20 and 40% of what's going on at the beach. Now, that's fine, but remember we're dealing with public health here, and public health scientists may consider a prediction of 20 to 40% of what's happening not really sufficient to tell the public how they should behave in public health terms, because there are real disease issues associated with bathing waters. Nothing like as serious as outlined by Paul, but we can be dealing with norovirus, 3 days off work, so there's an economic loss. And what my medical colleagues will tell me about norovirus is it will never kill you, it's a self-limiting illness, but you might want to die when you've got it. It's like those kind of problems, okay? And we've got various problems in modelling bathing water quality. I'm not going to take you down the list and start reading things at you, but basically that's the biggest. And that's if you get a value in a British beach of 100, your confidence intervals on that go from 50 to 180. You're only certain with 95% probability that your 100 value is inside the range 50 to 180. And we often forget this in environmental microbiology, how imprecise the things we're measuring are. And the policy community certainly has trouble grasping that in precision compared to, say, chemical parameters. And we realised we may have a problem at bathing waters with this kind of work. We've been playing around in the UK with microbial tracers for the last few years. Basically what they call dysphages, and they're viruses that infect bacteria. They're completely harmless to you or I. You can use them safely by tracing flow through water treatment works. They're that safe because they will just harm the bacteria, and many of them are based on viruses which infect coliform bacteria, called coliphages. And we can put maybe 10 to the 17 of these coliphages into the sea over a sewage outfall or into a river, and 10 to the 17 is equivalent to about 60,000 cubic metres of sewage if you're talking about the coliform bacteria concentration. So you can put a huge slug, a simulated slug, of sewage in the environment and look where it goes, basically. And you can put 4 or 5 of these in different sources, and you can measure the impact of 4 or 5 different pollution sources at an impacted bathing or shellfish water. Now, we did that in the island of Guernsey here, which you may know is a channel island just off the Normandy coast, about 11 miles off. Guernsey at the time had raw sewage discharges here and here, and those raw sewage discharges, conveniently, because it's got a very high tidal range, on a rising tide they shoot straight away and hit, the first landfall is in France. the question is, should we disinfect our sewage? And the results of the initial work was they weren't particularly keen. But we looked at 2 beaches here, and one of the things we were doing, one of the things we were doing with this work, because we were taking samples of these pharges every hour for 50 hours, so that's, it's a bit painful. But we said, well, why don't we just test for the fecal indicators at the same time? 2 beaches on this side of the island have no streams. This is a protected coast with sand dunes. There is no possibility that the sewage from here is getting round to these points. There was no pharge that we put in the sewage at those points. And these are the plots here of these 2 points. And this is the plot. Sorry, folks, it's me. This is the red here is enterococci, the blue is E. coli every hour. And what you can see from there, that's at 2 locations. What you can see there with a log axis on this axis here, we're getting from sort of zeros to log 3. We're going over 3 logs for sites that are definitely not sewage affected. We're getting this apparent diurnal, but I'm not saying it's regular diurnal, variation in the fecal indicators. Now, if that occurs at every beach, then going and sampling maybe a beach once a week for our bathing water compliance is clearly optimistic if we're aiming to get an assessment of the water quality at the beach. Some could say it was dangerous if we're trying to tell people on the basis of a water quality test the beach was safe. So that started the kernel of doubt in our minds. And we were very, very fortunate to be awarded quite a large grant, about €5 million of European money, to take this further and investigate it in detail. And what we did, we chose the most at-risk, if you like, borderline pass-fail beach in Wales. It's at Swansea, if any of you know the site. It's a very large, it's an urban beach. We've not got many urban beaches in Wales. I said the other day, we've got about 3 million people and 11 million sheep. It's very rural. It's very, very like, I think, like New Zealand in terms of its high stock densities, quite a small human population. But you've got a population here of about 300,000. It's the beach is entirely urban, very large river here coming in from agricultural areas, lots of CSOs in those rivers. So it was a good mixed location. And we did a series of investigations, which I'll not bore you with, but if it is interesting, if anyone would like the information, I can send you reports on this. So please get in touch and I'll send you reports over. But we, as part of that work, what we did was some fairly intensive sampling to investigate this variability. These are just the environmental health officers in Swansea who helped us on the work. And we sampled in the DSP, or designated sampling point, which goes in and out with the tide on a straight line. And we got this data. Now, please, I know it looks just like a lot of blue dots, and I'm pretty quite sad at getting excited about that kind of data. But if you just bear with me for a moment, those are the samples by GPS over the full bathing season. We sampled on 60 days, and we sampled on those 60 days at every half hour. Importantly, the coliforms and in enterococci were measured using triplicate filtration, which narrows down those error bars a lot that I've just shown you. That was a single filtration. What you should be looking at is each day is one line of blue dots. This axis here is a log axis. That's 1, 10, 100, 1,000. And what that data shows is that every day we're getting consistently, regardless of antecedent rainfall, a variability of between log 2 and log 3. That's 100 to 1,000-fold variability every day. And that seems, for Swansea, we've only got this data at this stage, remember, for Swansea. It seems alarming and remarkable. Because, first of all, it does suggest that our regulatory, and Britain's very intense in this, it takes a sample every week. Finland takes 4 samples a bathing season. And it suggests that that degree of sampling is probably inappropriate for any site that you've got large usage rates at. On the bottom axis here, this just shows the flow of one of the rivers going in. And interestingly, the range in the data, this 2 to 3 logs, is the same if it rains and it doesn't. It's got nothing to do with the rainfall input. What happens when it rains is, that's a particular rainfall event there. This day was affected by rainfall, and it's a bit higher than that day there. So it takes the mean value up a bit, but the variability stays as wide. So we tried to model that with a very simple statistical tool called multiple linear regression. And what we did, we used this rich data set, and we said we built up a data set of variables predicting what might be happening with just our own kind of background. And we had things like the sunshine. You know, does the sunshine kill bugs? It does on a butcher's slab. Does it in the sea? River flow. In rivers coming into the sea. The big rivers, I've just mentioned the big one there with a big catchment area behind it, had no effect. But a very small river, this thing, Brimmill Stream, which comes out of the urban area and is about as wide as this lectern. That had a big impact. But the best predictor was UV irradiance. Now this column's important because that tells us how much explained variance we're getting in the dependent variable. The dependent variable is the number of bugs in the sea, and these are the variables before we measured the bugs in the sea. So the most important thing was UV, and that explained 44%. With these things like stream flow, the maximum tide height on the day is just saying how much of the foreshore has been swept. This area in Britain has got the second highest tidal range in Europe after the Bay of Fundy in Canada. Sorry, in the world, after the Bay of Fundy in Canada. So you get about 3 kilometres on a spring tide and about 1.5 kilometres on a neap tide swept. All that swept area is getting seagull feces, and a seagull puts out as many E. coli a day in a person. So you could have quite strong animal inputs. So that was important. There's a bit of information on the sewage flow. There's just one sewage works. That's about 5 kilometres away. Wind speed might affect re-entrainment of bugs through waves, this sort of thing. And then we're getting one of the large rivers, again, not the immediately large river. The important number here, though, is this. Because using that simple prediction equation, we can get 80% explained variance. Now, we've only got that because this very, very detailed data set that we're using. Most of the work in America and most of the work in Britain by Scotland previously has been using the compliance data. That's the one sample a week in Britain, to build that kind of model. And generally speaking, you really struggle to get more than 40% there. But 80% is the sort of level where the medics might say, yeah, we could accept that in terms of public health warning. You've got some, if you like, if you're the Director of Public Health, your duty of care, you could argue, was being reasonably well protected with that sort of number. And we were very happy with that data. I mean, this just shows you, that's our model prediction. The blue and the dots seem to hit the line all the time. They seem to be at the bottom, but that's just because we sample during the day. And the time the water quality is worse is the middle of the night when there's no sun, basically. So, it seems to fit. If you look at it as a plot against here, the observed values and the model values here, that's what it looks like. That's what 80% explained variance looks like in a stats model. Okay. But we could also look at one other thing. And we started then to say, well, this diurnality, does it suggest we're getting different patterns of water quality through the day? And should we be using not just a prediction of the day, which is what is done in North America and Scotland, but can we say in real time, we'll predict what is happening and tell the public in real time? So we first started saying, well, what's happened to, say, morning against afternoon samples? This is the 3 fecal indicators, Escherichia coli, presumptive enterococci, and confirmed enterococci, morning, afternoon, morning, afternoon, morning, afternoon. Again, for the statisticians, the vertical bars are the 95% confidence intervals, so if that's normal data, parametric, if they are not overlapping, that's very statistically significant at the 95% level. So lesson there is, plan all your sampling for the afternoon if you want to fiddle the results. But what generally happens in the UK is we send out the people in the van to get the samples in the morning so we can get them to the lab in the afternoon. So we've been systematically forcing our beaches to a non-compliant position. It's worse than that because the van goes around the same way every time and takes maybe 10 samples. So they all start with the first beach, get to the last beach because that's the most efficient run. We've actually changed that now, so we mix it week after week, they go different directions. But there's some lessons there. And the effect, if you apply that to European standards for morning and afternoon sampling, if we got the morning samplings, we'd fail that beach, it would be poor, the afternoon sampling sufficient. Now, there have been various estimates on what is the value of bathing water to a local community per year, and it's in the 2 to 3 million when it's done. It'd probably be more for this one because it's a large urban area. So, these are quite important numbers. I must say that there's been no attempt by anybody in the UK to use this data to, if you like, cynically manipulate sampling times and regimes. But it actually gets a bit worse and a bit more convoluted, because if you do if you like midday and then evening, the midday samplings are really about, say, 11 till 3. I'll show you the data in a moment there. It is better. And that gives us the pattern with midday, the early morning, later evening will fail, it pass sufficient if you take midday. But we can actually do it hour by hour because we took, remember, half-hourly samples for 60 days. We've got a lot of data. With each of these hours has got more data in than the normal compliance calculation. And what you find is you get a pass against E. coli between 10 and 14. Most beaches in Britain and worldwide fail on enterococci, not E. coli. And we'd have sufficient, which is just passed. That's okay. It would still be legally passed. But we'd get good. So we'd actually, if we took all our samples between 14 and 15, we'd move up 2 full classes just by changing the sampling time. Again, that would be inappropriate and cynical, and nobody's suggesting that's done. But it just shows that this is if you like, a pattern that we're observing, which present regulatory regimes do not accommodate. And it suggests if you're going to predict for members of the public, your model must at least be able to reflect that kind of pattern, so you can give decent predictions to the public. Okay. We did test the model with a brand new data set in 2014, did the same thing again in terms of the sampling, which is the difficult stuff here, and the model was absolutely bang on and predicted the numbers in 2014. It seemed to be fair. It was a statistical model, so it's not causation, it's just giving you association, but it seemed to be robust after 3 years. But the next question is really, is Swansea an anomaly? Can a David Kay stand here and say to you, we should all be doing this because we found it at Swansea? Well, the answer is obviously no. It's a large urban beach and maybe very different than anywhere else. But I'm going to show you some data now which goes through to the 13th of September 2017. We were, again, very, very fortunate the European Commission gave us another parcel of money to take this work forward when they'd seen the initial results. And we're now working at a very different site. This is called Kemyce Bay in Anglesey. A lot easier to pronounce than Aberystwyth. And Kemyce Bay in Anglesey is a small rural beach here. A few fishing boats, a small community of hoteliers and guest houses who rely on this for their income because they get visitors in the summer. Very, very vociferous and articulate. So Kemyce Bay was unfortunate in that it was the only beach in Wales that failed the European Bathing Water Directive last year. Now the implications of that is they have to post the beach and put a sign up to say, do not bathe at this beach, or you're not advised to bathe at this beach. So you can imagine the local political willingness to do that, but they had to by law. Kemyce is here on the north shore of Anglesey. The other beach I showed you was on the bottom of Wales, at Swansea in the Severn Estuary. And that was the sign they had to put up. Don't worry about reading it, but it's there on the set if you want to see it. But that basically says, "Here be dragons," to the potential recreators. And that's got to be, every beach has to have this kind of information centre manned by the Environment Agency for a Euro beach. So it's very much up front. That shows the little town of Kemyce. It's tiny. It's a population of a few hundred. It's absolutely tiny. It's rural, mainly sheep farming. This shows the designated sampling point, like you saw at Swansea with the GPS references going in and out. And we monitor the meteorology and stream flow going into the bathing water here. We've got a second backup meteorology station and stream gauges. This is idyllic rural Wales. For the first time ever, we've had 3 full sets of stream level devices pinched, and we can't understand why, because nobody could ever sell them or use them, but anyway, they've gone. We've worked in some very, very challenging urban environments in the past, in Liverpool, in Southend. We've never had one piece of equipment go until we started working in rural West Wales. But these are the samplers going out every half hour. It's challenging work to sample, and I'll run past these so we can explain it to you. But they've got, this is the DPS, designated sampling point for this year, the tidal in and out samples, each sample is logged. Now, E. coli. To cut to the end of the story, this is the log axis. That's a day. You can see it goes up then. But the range is, let's say, 1, 2, 3, nearly 4. Range here, 1, 2, nearly 3. The range here, and we've not done the stats on this yet because people are still sampling today until the 26th. But the range is exactly the same as Swansea. This is the sample points for the enterococci. Range, exactly the same as Swansea. So we're getting an almost identical picture on 2 very, very different beaches. Not, They're at-risk beaches, but they're not terribly bad. They're not grossly polluted beaches. You know, we do have beaches in Britain where all the numbers are above the maximum level. You know, these numbers occasionally reach the maximum level, just enough to fail the beach. So initially, we think we've got an observation there that may be a lot more generic if you start looking at the daily patterns. And at the moment, all of the WHO and the EU interpretation of the WHO, in terms of prediction, is made on the assumption that we can make predictions using the compliance data, i.e., that assumption inherent in it statistically is that the compliance data characterizes the day on which it was taken. This says it doesn't. So this is why I wanted to present data which is challenging us, basically to see if anybody had any ideas what the hell we should do with it. You know, we do have a problem. I mean, just the other sort of things we might predict from, this is turbidity. And if sunlight is killing bugs, turbidity stops the sunlight getting at the bugs. So the hydrodynamic modelers can maybe use this kind of data to come up with a hydrodynamic model of real-time prediction of kill. And that's one of the things we're thinking about. Salinity kills bugs. So we're getting variability in salinity, and we're looking at that in terms of tidal ranges. And we've got that kind of physico-chemical parameter data to try and aid the prediction process. There's the inputs coming in from the streams. So, you know, we've got input data to use. These are 3 stream inputs against the flow record. You know, you get high numbers when you get high flow. And you can see low flow, it's down here, 100. High flow, it's up here between 1,000 and 10,000. I mentioned a couple of days ago this kind of 3-4 log change on high flows over minutes. So that's a really episodic input when you put the flow in, which might go up by tenfold. Okay, so tentative conclusions. Spot measurements, that's what we do now. We take a spot measurement to get compliance. Can't index bathing day risk. And that knocks out the calibration data for most models that have been produced to date, whether they be infrastructure models, hydrodynamic models done by the big engineering consultancies for the water industry. It certainly knocks out the prediction models that we've been using for previous compliance and public health warnings. Next question, and we're very fortunate. I may not have time to show you these data, but we put a lot of effort in Swansea into generating the background data for hydrodynamic models. So we had 4 simultaneous deployments of bed-mounted ADCPs. We had boat-mounted ADCPs. We did 5 tracer studies using 4 releases, each time of different tracers. So we were monitoring connectivity, drogues, dyes, a lot. We gave the hydrodynamic modelers everything they wanted. They were colleagues of mine from Cardiff University. Roger Falconer ran it, and Reza Adamen. And Roger, you know, he was the president of the International Hydraulics Research Association. So, good people with a lot of experience. And we ran hydrodynamic models and gave them all the data, including the very detailed data at the beach, and said, can you predict or simulate that with your hydrodynamic models? Because remember, I'm giving you here some very simple black box multiple linear regression models, which you might say, well, they're far too simplistic to do the job. But hydrodynamic models are process-based and mathematical. I'll just cut to the quick on this, and that is the attempt of the hydrodynamic model to predict the points water quality at the bathing water. Now that's a bad picture, because I didn't want to waste all of your time here. What the hydrodynamic model does very well, it predicts the daily geometric mean value, but it can't accommodate the within-day variability. And those of you who can know what you're looking at there, I mentioned 80% explained variance. If we got 80, at that point, 0.9 is 9%. So we're getting about 9% here, but it's not significant. And we did it 2 ways. One, trying to predict where the nearest cell in the model to the point was, and where the nearest cell in the model to the line of the DSP was. That's the closest point. That's the DSP transect. So we did, tried to do it in different ways with the hydrodynamic models, but neither could get anywhere near it. Leading us to say, my colleagues who are, if you like, research scientists using hydrodynamic models, very pleased with that, because if the next challenge is to get the hydrodynamics to work to predict those points within the day, is that within day variability that's the big challenge, then clearly they've got the next research project sorted out. Not to be too cynical, but that's where in my view we've got to go with the hydrodynamic modelling. I know, Chairman, we're getting close to 10 o'clock. Would you like me to pull this to a draw now? Because that would sorry? I'd happily take some questions, yeah.
Yeah, we are getting close to 10. We're a little bit delayed, but look, a fantastic presentation. And should you ever ask me would I like to go swimming with you? No. Unless it's 2 o'clock. So, does anyone have any questions? We do have some time for questions because I suspect that, there will be quite a few. We'll take sort of 5 minutes of questions and take 5 minutes off your morning tea, making a unilateral decision. So, go there and then to you, sir.
Arash from University of Auckland here.
Sorry, folks. Thanks.
All these results published.
Basically, no. But this is why I said to start with, if anybody would like the reports, because all the public reports have been done and they've been submitted to the Commission. Now, our big push to we only finished the one project last year, we started the next one, was to get all those finished reports into the Commission because, I mean, put brutally, if we hadn't have done that, we would not get any more funding from the European Commission. We've got papers now prepared for publication, which will be going out shortly. There'll be a separate paper on the hydrodynamic modelling, a separate paper on the regression modelling. They're all prepared, ready to go. We're just circulating through the team at the moment. Certainly, the thing that's exciting me most, which may be sad, but the thing that's exciting me most is the fact that we're getting replicate patterns occurring at Chemnice Bay. And as I say, we've not got the data in for that, so none of that is even in report form yet. I was just sharing it with you here so you can see where we're going.
And then it was over to this gentleman here.
Sorry folks, the lights are, I can't see very well.
Hi, thanks very much. Dr. Simon Tannock from Alga Enviro. Given that you're struggling with the inter-day data, wouldn't use of real-time online monitoring of E. coli turbidity and things like that be of value?
Sure. We've tried enzyme-based systems previously, and it would be very interesting for this sort of work because we are using the triplicate filtration. We've got very precise estimates. We're using large volume samples as well, so we're doing membrane filtration and we've got the best precision we can get on that. So it would be a very good, we can't do it now because it's gone, but the European funding that we've got is for the next 4 years, and what we're going to do is do another 3 beaches at least in Wales on the site with the same protocol. But to be honest, our choice is going to be driven by which beaches are most at risk, because we're going to the funding is with what's called European structural funds, so it's about helping the economy of local communities. So we're trying to stop these local communities closing their beaches. So what I'm saying is there is the potential there for a very good data set against which to test the enzyme or any other real-time systems. We're doing some work with a couple of our water companies in this general area, and we have used some of the enzyme systems. There's some probe systems that are available. And we've not found at the moment we're getting very good correlation with spot determinations using membrane filtration. I'm not saying one is right and one is wrong, but there's a lot of intercomparability work that we need to do on the new systems. But if we could get real time, it would be great. And the Americans certainly in this kind of work are using real-time sons on buoys to try, as well as sampling. And they're taking readings early morning to say whether the beach should or should not stay open during the day. Now, at the moment, my view is that's probably wrong, and there are American scientists who say the same. Because if you get a sample, say, at 7 o'clock, and you get a result very quickly, as is possible today, and you got a result at 9 o'clock, and you decide what you're doing for the full day, it may just be that your 7 o'clock sample was particularly bad because it had been nighttime before you took your sample. So I think there are better ways to use the real time. And what we're doing at Swansea, for example, now, we're issuing 3 warnings during the day, but we may move to an hourly warning as you go through the day. So where the beach might not be used in the morning when nobody's there anyway, it might get used in the mid-afternoon when more people want to go, that sort of thing. So that's where the enzymes, or the real-time systems may come in better.
Can I just add to that? We're doing work in Australia where we're doing real-time with Spectro, measuring E. coli and things like that every 2 minutes. So
yeah. It's what's needed. Yeah.
It's proving really, really valuable.
Good.
Just here.
Clive Rundle from Beaker here. Fascinating, absolutely fascinating. I think you've got us all spellbound. This isn't going to help with the regulatory challenge, but I wonder if in the public health management arena, whether there's a role for artificial intelligence here in spotting the patterns between what are really just a whole bunch of environmental factors that you're identifying are are relevant.
Absolutely. I mean, it's something we've got colleagues working on now with the Swansea data. For example, the other approach that's being used now in other parts of the world is decision trees rather than the MLR. And some colleagues are putting forward sort of Bayesian belief networks as another method. So, we've opened up, if you like, a series of testing opportunities with the data set that we've got, and that's what we're trying to pull forward. But I take your point entirely. We need IT.
Right, we'll just go with one more just here. And David is around for morning tea, I think, as well, aren't you, for questions?
David, Liam Foster from Opus. A heck of a lot of investment has been put into the wastewater infrastructure through the various AMP periods as a result of the Bathing Water Directive. Is that regretted now?
Well, I would honestly say not at all. I think what the Bathing Water Directive has done, because it used the WHO work, which is, I think, correct in terms of its prediction of illness and its dose-response relationships. The problem we've got is the assumption that the regulatory tools at the bathing waters would give us that quality for that day, and that was what the prediction models were required for the prediction models to work properly. But the epidemiology that underpins the WHO work and the EU directive standard was samples taken at the time and place of exposure. And again, using triplicate filtration, so they're quite accurate. So I feel quite comfortable with the dose-response relationships. I feel uncomfortable that our regulatory system is giving us a tool which lets us characterise the water quality which predicts health. So I think we've got part of it right, but the regulatory tools need redesign in some way, and that's the bit that it's still confusing me, quite honestly.
All right, and I think, was there one pressing question just there? And this will be the last one.
Graham McBride, NIWA. Are we underestimating risk because the control cohort design doesn't include children?
Absolutely, Graham. If I could just, it's a very good question. Just for the general audience, the British work was done, and we were putting in applications to national NHS ethics committees. Okay. Now, if you like, at the time, I was an academic working for the government to come to to design a protocol, and we were risk averse. So we put in a protocol to, it was actually Sir Douglas Black who chaired the committee in the United Kingdom. And we took out children. We didn't feel that there would be permission to use children as part of a healthy volunteer experiment. Now, just to give you one of our national Sunday newspapers, we had a DEFRA meeting on our DOE at the time. It was Department of the Environment. They were funding the work. Had a meeting on the Monday. The Sunday paper had a headline on the first page saying UK government sponsors Nazi-style experiment, because what we were asking was people to go to a beach and bathe as they normally would, but it was felt there was some kind of coercion. There was no coercion. It was randomised control. Now, Douglas Black, our application to go through with no children, it sailed through. And he actually, we didn't speak to him at the time. We were just very grateful to get it and get the work done. But we later on spoke with him and members of his committee, and the word they used is, why were you so concerned about not using children? You know, their term was, you'd be straining at a gnat not to use children, because that would have asked people to do what they would normally do as part of their normal daily activity. And we do find some children, even on British beaches. So, you know, his view was we were silly. But we were probably too frightened for the whole thing to be rejected and not be able to go forward. So we took a very conservative line. Now, the work was then replicated by Albrecht Weidemann, funded by the German government, on freshwaters about 3 years later, and he was able to use children no problem. And then again, for the European work with the Spanish and the Hungarians, they also included children. What we didn't find in the child cohort with that work was a big excess over the parental. It seemed to be, you know, similar in many respects. But having said that, I must state to you that what we found is, because of the intervening period, the quality of water at the Spanish and Hungarian beaches was generally better than it had been previously at the British beaches. I think because the sewage treatment system had improved over the period. Most of the Spanish beaches, for example, had UV disinfection, which none of the British beaches did that we looked at. Indeed, the British beaches, it was quite common at the time to discharge raw sewage through long outfalls. So you had a very different sewage disposal picture. It was quite difficult in the later European work in Spain and Hungary to get much information on high exposure levels. Okay.
Fantastic. Ladies and gentlemen, please a round of applause for David Kay. Thank you, David. Here we go. A lovely bottle of